Good afternoon, everyone. I'm Stefano from Nokia Labs. I'm working for the research for the standardization, and this talk today is related to a study item that was discussed in 3GPP for 2 years now, and is related to the evaluation of extended reality in 5G NR and beyond, because now 5G is evolving toward 5G advanced. So first of all, let me briefly introduce the outline of the presentation. I will start by introducing the technology of extended reality and the challenges, and then I will discuss also why 3GPP is interested in extended reality, and also the timeline of the study items within the 3GPP. Then I will discuss the evaluation that has been done during the release 17. During the release 17 of 3GPP, there were a few study items, and one specifically run for the evaluation of the impact of XR services on the radio interface of mobile networks. And I will briefly discuss the traffic model, the KPI, and the deployment scenario that have been considered, and also the results. All these evaluation also generated several discussions related to potential enhancements for the radio interface and the feature of the radio interface. And in particular, the focus of the studies was mainly on enhancing power saving schemes, and also capacity feature that help to improve the capacity. Capacity, as we will see, defined for XR services, and we will see that it includes also a quality of service metric. Is not just the raw throughput. In particular, I will focus on one specific enhancement. There are many more that have been discussed, but given the time, I will focus on a specific enhancement that is, and on a specific feature for power saving, that is the DRX discontinuous reception, is a duty cycle basically. And what we have, what is our proposal also for the evolution of DRX in adaptive DRX. And then I will show some of the results that indeed show the benefit of using some adaptation in this type of duty cycle scheme. And eventually I will conclude the presentation with some key takeaways. So what is XR? Well, it's a general term. So XR stands for extended reality, but it's an umbrella term. It includes several types of different services. Among these services, there is virtual reality, augmented reality, and mixed reality. In virtual reality is services in which you have you are immersed in this virtual world. Someone call it Metaverse. In augmented reality, there is a bit more interaction with the real world, because you capture also the surrounding environment, and this is sent to a server, and the server then augment this with, for example, by adding information or objects, virtual object on what you are looking at. And then there is mixed reality that instead introduce also haptics, so the possibility to feel with the world, the virtual world around you. So all these services, as we will see, introduce different type of requirements, because the architecture to implement these services are kind of distributed. So it's not the application running only on the headset device of the user, but is involve also the communication with a remote server. So you have basically an exchange of information across between the device and the server. Cloud gaming is also included in this umbrella because it uses technology that is very similar to the one of virtual reality and extended reality. One of the key features for this type of services is that they introduce this viewport-dependent streaming. We'll see why this is important. Basically, the idea is that instead of sending the entire 360-degree to the user, you send only the portion of the space that the user is looking at. But to know what is the part of the 3D space at which the user is looking at, you need to send this information. This information is called pose information, and is basically the representation of the head position and head orientation. So you have the three X, Y, and Z coordinates and triangle of rotation. It's also called in the literature 6 degree of freedom because you have also this information. So based on the information, you can understand what the user is looking at, and then you send the information with certain different quality to the user so that you can stream basically the content. And this required for an interaction between the user and the server. There are different protocols.
Yeah. Sorry, I just have a question for this use case. So what is the time delay?
Yeah, we will discuss this because they are important for the evaluation in 3GPP. Indeed, there has been several discussions, just a rule of thumb. You can consider from 10 to 15 milliseconds of a one-way delay. So the round trip time is usually bounded always below the 100 milliseconds, but in certain cases even lower, considering also the processing that you need. Yeah, otherwise, yeah, indeed, it creates also problems. But there are many components inside. So what you call delay that's been in the different study items of 3GPP, there were a good definition of the different type of delays, because there is what is called motion to photon delay. So when basically you move your head and the information is displayed in front of your eyes, basically. But these include both transmission delay and computational delay. So this has been reduced to consider only transmission delay, because of course in 3GPP we focus only on the definition of the transmission part. So after
specific when you say delay, is it just a measure of the FH delay? Let's say like the bandwidth required. Sometimes the delay
it's a bound. It's a bound that you need to consider. I mean, the fact that you can send faster than that bound is fine, but if you are above that bound, then
do you consider, for example, jitter?
Yeah, there is also jitter inside. We will see the model that has been considered, because there are different discussion also regarding
different measure.
Yeah,
sometimes we also say initial access delay.
Yeah, it's not a constant. You have something that varies across. Yeah, and then depends also on the transport protocol. This delay may vary according to different type of things, because if you're streaming a 3D video, for example, the delay, it's the notion of delay depends also on the type of protocol that you're using. So, for example, you can download if you're using kind of dash protocol. Usually, you're downloading piece of the video, so segments of the video that you have already stored in your device, and then you're keeping those for with certain delay. So the delay becomes less critical. But when you need to interact with the environments that you have around you, you need to consider that the information is sent to the server. The server process the information and send you back a video based on the commands that you have sent, or the pose information that you have sent, or even a picture that you have taken to overlay some object to what you're seeing. So all these things are basically included in the evaluation of the delay, so that you give a bound for the different components for transmission, processing, and displaying also, because also that has some impact. So considering from a high level perspective, the different type of traffic flow that you have in upstream and in downstream. Yeah, before that, I have to mention that you cannot actually execute all the processing in the headset device for several reasons. First of all, because these processing techniques are quite energy consuming, so you cannot execute on your headset or your glasses, smart glasses, this processing. So the processing is always done in the network, and therefore you have a communication between the server and the client. That is called split rendering architecture. Someone call it split chip because it's not just the rendering that is sent, that is not only the rendering function that is executed remotely, but there are several other things that are executed remotely. So the two type of traffic that you can have in uplink and downlink, then is typically pose and control information, very tiny information that is sent periodically to the server, and then the server generate basically a video, 3D, two video stream basically that are different angles, and then when are displayed at the same device, they give you the impression of this 3D world. So you have a lot of data that is sending downlink. The other possibility for augmented reality is instead that you are not just sending the pose information, but also a video, a downscaled version of the video, and this video then is augmented. For this reason, we talk about augmented reality, because you had on top of this video several information. For example, this can be useful for training, in which you overlay, for example, some tools to guide and to train people for several employees for several type of tasks. So you can remotely train them instead of asking them to follow a training in real training. So the model, in this talk, I will focus on the first part of the pose information and the video, and the evaluation has been done also for the other, of course, but I will mainly focus on the first part because it's also the more general. So when we discuss about XR several times, we see that we are discussing about delay and also reliability. So these two metrics are taken into account in the evaluation, but this type of traffic is not the same as industrial automation, what is called industrial IoT, or this type of traffic that require ultra reliable low latency communication. For XR, we have latency constraints and reliability constraints that are much smaller than the IoT, for example. But given the high amount of data that you're sending, this constraint becomes challenging to be satisfied, because eventually you still need to use resources to guarantee the delay and the reliability budget. So eventually these constraints enter due to the fact that you have a volume of data that you have to send that is much larger than what you have considered for industrial application instead. And the other also important things that you need to consider is that this type of traffic is the model that has been devised in pre-GPP that has been considered, considering also real traces, is that is a quasi-periodic traffic. So it's not exactly periodic. There is also this jitter that is taken into account, but is bounded. The traffic arrive in bursts, large bursts that need to be satisfied, and then the order of the variabilities of the size can be also up to 3 times. You have also the interactivity, so you have simultaneous transmission in downlink and uplink, and you have also this concept of interactivity that is important to take into consideration. So that's more important for capacity. So the fact that you can satisfy user in downlink. So when you do your evaluation, you need to consider really the uplink and the downlink, for example, for the capacity to be able to see what many users you can satisfy in your system. So as I say, the brief outline of the timeline of pre-GPP and the evaluation of pre-GPP. So you see pre-GPP about 4 releases, and then a certain, usually with a pace of 10 years, you have a new release that came out, and it's called a new generation of wireless technology. So we have just passed the 5G. Now we are in the middle of 5G advanced. So this release 18, 19, and 20 will be the release that will contribute to the definition of what will be 5G advanced. And as you see, the XR is considered one of these killer applications for 5G, in the sense that requires some enhancements to be supported. Vanilla 5G is able to support, as we will see, XR services, but still certain requirements are needed to if you want to increase capacity, and if you also want to monetize basically the investment for handling this type of services. The study concluded with release 17 at the end of 2000, in the middle of 2022, end of 2023. There was still a part of discussion in release 18, and now there are more deeper discussion about possible enhancements, not only from the radio interface part, but also the architecture. So also the architecture of the network needs some improvement in order to support these services. But I will focus in this discussion about RAN. So let's move on and just discuss the evaluation of XR in 5G and NR, and also the traffic and the metrics that have been considered for the evaluation. So the traffic model that has been considered for the evaluation is this type of traffic. So you have basically frames or video frames that are generated periodically with a certain periodicity. These frames then, of course, are delivered as a burst of packets. But what is interesting for, I would say, the source generators to generate this type of traffic for downlink. So the upper part represents the 3D video in downlink that is generated with a certain periodicity. The thing is that the traffic doesn't arrive periodically at the genome. There are codec reason, and the codec actually introduce some jitter because they are generating frames with a certain periodicity, but they need some computational processing. And then you have also the delay of the transport network. So at the genome B, you don't have frames that arrive exactly every 16.6 milliseconds in case you are using 60 frames per second. So you have this burst of packets that arrive more or less at 16.67 milliseconds plus some jitter. Several evaluations have been done by also other companies. Eventually, the agreement was to have this jitter bounded between -4 and +4 milliseconds. That was something that was reasonable, good to take into consideration several type of application and several type of video type. For uplink, instead, you have the pose information. We will see that the pose information has a very tiny information that is sent periodically by the device, and this also the periodicity is more easy to control, so you don't have this jitter like for the video trace in downlink. So we haven't modeled the jitter in downlink. In uplink, sorry. Then there is also the size that is important. Also the size. So this you have a variability here, as I show for that move shifts the frame arrival in the time, and then you have a variability also for the frame size. So even the frame size has a variability, and is still bounded between a maximum and a minimum with a certain distribution.
Another question. So you don't have a different data frame in Vocoder?
Well, you have different. We didn't focus on the type of frames. We just evaluated traces of traffic, also other companies, and then we define from the bitrate what is the average size of the bars that arrive. But these bars varied a lot according to the type of coding that you're using. So you can have a coding that is based on slice, or coding that is based on base layer, enhancement layer, and so on. So you can have different kind of things. Yeah.
So because when you have different data frame, there is an order of magnitude of size between the key frame, which basically is a JPEG, and the data frame just spots the difference between the previous.
Yeah, exactly. But today, at the beginning, the discussion was mainly about this iframe and pframe, and in XR, B frame does not exist. So the codec doesn't generate this B frame because you don't have the possibility to wait until receiving all the frame that need to be decoded. Usually they use only I and P frame, but nowadays they are not using any more frames. They are using slices. So you just basically have in your picture, you have a slice, slice or strips basically, or kind of, and they are refreshed with, so each new frame brings a new I slice in round robin fashion, and so in this way you get guarantee that the rate is more smooth. Yeah.
So there is no adaptive coding of things of this kind?
There is adaptive coding, yeah. It is not considered because the time that we have considered for the evaluation is rather short. But we don't consider so we consider fixed frame rate and fixed quality. So, for example, for the quality, what has been noticed is that you have different type of quality, and these are an effect directly on the bit rate. They were considering this 30 megabit per second and 45 megabit per second because many from the traces we are seeing that usually you have for full HD you have 30 megabit per second as average, and for 4K 45 megabit per second at 60 frames per second. If you scale up with the frame, then you scale up also with the rate. You scale down the same, then you can play on the resolution or on the frame rate. And this actually was not discussed because defining a model for this is really dependent on the application. So you cannot really define a model that is valid for the whole type of application. So we focused our attention on a fixed scenario. And of course, then you have to consider also this allowed to evaluate how many users you can support with certain characteristics. But then, of course, with adaptation, you can play more. Then what else? Yeah, the jitter, I said, yeah, and this. So everything in the evaluation is static, but of course, all the other parameters of the simulator that we use it's all dynamic. So the evaluation was considering three main key performance indicators, three metrics, I would say: capacity, power consumption, mobility, and coverage. Eventually, the main discussion was on capacity and power consumption. Mobility and coverage was evaluated, but there was no interest for evolution for mobility and coverage for at least this release. So the main focus of the analysis was on capacity, and the capacity has been defined as number of satisfied UE that can be satisfied by the 5G NR. And satisfied UE is UE for which 99% of the frame can be delivered within the packet delay budget, and the packet delay budget were considered two that are indicative for cloud gaming or virtual reality or augmented reality are 10 milliseconds or 15 milliseconds. One way, so in downlink, for example, and in uplink are slightly different, but you can consider this also for uplink. Then there are also, of course,
one thing I do not get. I mean, what does it mean? Proportion of I mean, so you need a load model, right? So you have your. I mean, if there is a large number of users to which you do the XR.
Yeah.
I mean, satisfying 90% of a large population is one thing. If there is only one, so I mean, what I don't understand is how you entangle that with.
Yeah, basically,
load, right?
yeah, we increase the load of the network, and we see how many so you have a certain number of cells.
Okay.
So you generate, yeah, exactly. You generate a certain number of cells. You increase the load, and you see when the system is not able to satisfy any more user, and that is your maximum.
I get it. Yeah. Thank you.
And to mark a user as satisfied, you need to at least send 99% of the frame within packet image and the packet image. So that means that you generate 60 frames per second. So it means that every 2 seconds you can delay just one frame. That's the idea for each user. And if you delay too, then the user is not satisfied. Of course, we run longer simulation, but eventually that's the evaluation. Then for the power saving, there are also other KPI of interest, but this was the definition of the capacity that includes this reliability, because frame that is delayed beyond the packet delay budget is considered lost. So loss can be modeled as an infinite delay, and eventually there is this reliability that connects the delay and the capacity in terms of number of satisfied users. Then for the power consumption, the baseline, of course, was always on. This give you the upper bound of the user that you can satisfy, but power saving was important because this type of services, of course, are battery constraints in the sense that you want to extend the battery life, but there is also another reason, that is the heat dissipation. You are wearing this device on your head, and if they become hot because they are consuming, then the comfort of the user is not anymore. So the idea of using also power saving scheme is important, because eventually you want really to try to minimize the power that is consumed by this device, for both for battery lifetime, so extending the lifetime of your device, and also comfort for the user. So there are several evaluations that have been done for power saving scheme, and one of these is the discontinuous reception, but there are also many others. I will focus on the analysis of the discontinuous reception. That is the main one for the main feature for power saving in the radio interface. The evaluation was done in different scenarios to consider the typical scenario in which companies think that the services will be deployed. Is the indoor scenario. So you have 12 base stations basically in a area of with 20 meters of intersite distance. So each cell is away from the next one by 20 meters, and the antenna is 3 meters to model basically a room or a big open space. And then there is the dense urban scenario, in which instead you have outdoor scenario, in which the intersite distance is 200 meters. The cells are deployed in an hexagonal fashion, and you have 3 sectors per cell. So you have 7 base stations and 3 cells for each base station. So you have 21 sectors basically that are called cell according to the terminology of 5G. You need you have considered different frequency, different frame structure. Frequency was both in FR1 and FR2, so below 6 gigahertz and above 6 gigahertz. The system that was taken into account was TDD. This is important because you have reserve resources for downlink and reserve resources for uplink. The frame was this one that repeat. S is basically a special symbol that you need to have to switch from a downlink to uplink, in which you can still use a portion of it for downlink, but not the entire symbol is used for downlink. Then we have other parameters that affect the capacity, and the is the scheduler. For the scheduler, we have considered proportional fairness, typical. The blur target of the transmissional layer 2, so the block error probability was 10%. This is important because lower blur target, you cannot select high order modulation coding scheme, so meaning that your rate is limited, the transmission rate, and therefore if you are too strict with the blur target, then you may not be able to exploit all the rate that you have available. And then the other, of course, the problem is that you may have errors, so you have retransmission, but it's better to have an error retransmit faster than, as we have seen, than having instead a lower blur target. And then, okay, there are other parameters, but are mainly related to the design of the antenna, of the UE and the aging of the.
What are the propagation assumptions? So since you use also millimeter waves,
yeah, we use the obstacle. There is, of course, the interference. There is no obstacle in this area in the sense that you don't introduce. Actually, in the outdoor scenario, there are a portion of users that are indoor and a portion of users that are outdoor. So there is a factor that is introduced for those users that are selected indoor that multiply basically the data to the path loss and multiply it. So you have a factor actually taking into account this. So, but these are the only obstacles that were considered in the evaluation. And the antenna in FR1, we have considered a single panel for the user. This actually has an effect, as we will see. Instead, for the FR2 in the millimeter wave scenario, you have 3 panels that are on the 2 sides of the device and on top of the device. This is important because in the indoor scenario, you have the antenna that point downwards. So you will see that this actually helped in the performance. And instead, in FR1, we used a single panel antenna. And of course, even if you are indoor, you will see that it's not so nice, the propagation environment. In FR2, instead, we still have MIMO multiple antennas also in the base station, but we have an hybrid solution for the MIMO. There are several parameters that change, but you will see that the physical layer parameters, except for like the position of the antennas and so on, does not affect too much the performance in terms of application layer. Of course, you have better propagation, but this does not necessarily reflect in higher number of users that are satisfied. So there are other things that affect more, like the scheduler, for example, the blur target. Of course, the modulation encoding scheme that you are using, and of course, by scheduler, I mean also if you are using a multi-user MIMO or a single-user MIMO, you have more or less users that you can satisfy. So that's in the results that I show you. I will show you only single-user MIMO. So when I talk about cloud gaming, I'm considering the 30 megabit per second and 15 milliseconds of packet delay budget for the metric to decide if a user is satisfied or not. For AR and VR is 30 megabit per second, 10 milliseconds, or 45 megabit per second at 10 milliseconds, depending whether you're using full HD or 4K resolution. First things in the indoor, as I told you, you see that you have around 5 users per cell that you can satisfy for the cloud gaming. But when you move to FR2, you have much more. You double. The reason was basically the fact that how we define the scenario. The scenario in the indoor is, as I said, you have just one single antenna that is pointing on one side of the user. Instead, the antenna is on top. And in FR1, you don't have also these nice beams that you can get in FR2 that are pointing more towards the user, so you can reduce also interference. So there is a combination of effects that actually improve the capacity in terms of satisfied user and in terms of propagation for the user that are not easy to obtain in FR1 with the parameter of the antenna that we have considered.
One question: when you say I'm still puzzled by the notion of satisfied user.
Okay.
I mean, do you use, for instance, you say 4 or 5? Okay.
Yeah.
So do you deny the access of the others, or do they still transmit? Does one still transmit to these users by creating interference?
They are still transmitting.
So
in the evaluation, they are still transmitting, but they are marked as not satisfied because they are not.
Okay.
So we don't try to do admission control. Yeah.
Okay, because you could improve on that.
Yeah, exactly. Yeah.
Stop those.
Indeed. If you start adding admission control, then you can improve the performance, but that was not considered in the evaluation, because in a certain sense you will not be any more proportional fair, but you will like be giving priority to those users, and then you are basically like removing from the system those. Of course, if you want to like stabilize the system, you need to remove those users eventually, but that was not the goal of the evaluation.
Yeah, and so, and if you so perhaps it's linked to proportional fairness, right? Yeah. But where are located those satisfied probably close to the base station?
They mostly are the ones that are close to the base station. Okay. So you tend to be fair in sense of resource allocation, but you are geographically unfair.
Okay.
Yeah, we have seen indeed the decoupling gain was also something that was not so much evaluated, the coverage, because indeed when you are very far away and you are on the edge of the cell, of course you get less rate, and then you take more radio resources. That means that you have somehow you still, the scheduler try to be fair with you, but eventually it cannot provide the same kind of resource unless you start to include some notion of application awareness in the scheduler, so that you try to consider also this notion of capacity.
And so in this evaluation, do you also have the usual guide, maybe a phone call? Or
we haven't considered that. We have considered only homogeneous traffic, so only XR traffic basically. There has been evaluation internally for mixed traffic. The first focus of the free UVP was only to evaluate really the bulk performance, and then see how we can improve later on, and if you have to consider also mixed traffic. It's not mixed traffic affect the capacity to a certain extent, but usually if you have like what is called EMBB traffic, so people that surf internet, for example, that has a lower priority with respect to XR, and therefore in a certain sense the scheduler will try to avoid to give resources to the user if you're serving XR user. So in any case, you may still have the interference from another cell because you cannot control the other cell. That's, of course, that's still there. And you will see a gap, but is still the fact that you give priority on average is not affecting so much. But there is a gap.
Just I forgot what CG means.
Cloud gaming. So, but it's the same. It's the same technology, same type of traffic eventually. So then in FR1, sorry, in dense urban, instead we have results that are more similar. Here in this case, you have free antenna panel. Sorry, you have the user in us. First of all, the user are far away from the base station. Then the fact that you have also a single panel is not affecting so much, because you, in any case, the base station is far away from you, so it's not on top of your head most of the time. So this actually helps with the propagation, and there are other effects that are affecting more the capacity than the propagation in the server. You have, for example, this kind of obstacle, the fact that you have the path loss that change in a discontinuous way when you enter in the indoor scenario.
I have a question. Once you introduce mobility, does this solution include mobility once the user moves from the center of the cell to the edge?
Yes, we have done some evaluation, and actually we have the things that affect more at least the capacity of a single user. We haven't evaluated for many users. It's the speed, because when you move from one cell to another cell, you have an handover. And in that handover, is where you basically are losing, you may lose the frame. If your speed is larger than a certain value, usually, so if you want to bound the frame losses to this 1%, you need to bound the speed of the velocity at which the user is moving.
The loss of performance due to velocity is linked to the multi-panel thing and the beamforming.
It's mainly, yeah, it depends, of course, it depends if it's due to the mobility. It can be intra-cell mobility or inter-cell mobility. Inter-cell mobility is more challenging because you're moving from one base station to another base station. So you need to basically be able to perform the handover, the full handover procedure before basically being disconnected and losing the frame or introducing extra delay. So if your speed is limited, all this operation can be done in such a way that you don't lose connection. There are features that have been introduced in FR2 for having basically when you have multiple antennas, so multiple panels, you can be connected to two base stations. So you can be connected to what is called master cell and the secondary cell. In that case, you can actually try to reroute basically the traffic in such a way that you don't lose connectivity. But this is not fully integrated.
I'm sorry. I have a question. How do you, in your evaluation, define the latency, for example, for cloud gaming or for the remote rendering? For cloud gaming, you have maybe some backbone connection with some other providers, or for the remote rendering, you consider the closest edge computing server?
This is the budget only for the radio interface. So it doesn't consider other. So we took this, like in certain cases, depending on the application,
the base station and the user.
All in all, the round trip delay is usually 100 milliseconds. So if you have these 50 milliseconds of delay, one-way delay, if you want to keep the same. And from this, basically, since we know
Plus
that this server you reduce every component, and then you assign this 10 milliseconds, 50 milliseconds to the radio interface. Of course, you could be more, I would say, dynamic in assigning the delay to the different portion of the network. But of course, everyone wants to get more because that will be simplified the life of everyone. But there are things that you cannot really. So there is a fixed latency, for example, in the core network that is there, you cannot reduce it more than that.
So that's fixed.
So you cannot reduce more than that. And then there are processing delay are bounded as well. Then for the uplink capacity, this was considering just 20% of the radio frame dedicated to uplink transmission. So 1 out of 5 slots for uplink. You can see that pose doesn't introduce any problem. So for the pose information, you can satisfy 50. This was not even optimizing the configuration of the network. So you can satisfy 60 users per cell in all scenarios. Instead, when you start transmitting traffic, the video traffic actually for uplink is downscaled to 10 megabits per second. When you start transmitting video traffic, instead, you see that the number of users that you can satisfy are around 5, 6, no more than that. So for the AR, actually the uplink count, it's becoming also the bottom. So for power saving, I will try to be quick. This maybe is a part where I could dedicate a bit more time. But anyway, the DRX works. Is a duty cycle. I think that most of the people know. So you alternate between period of on and off. That's the idea. To define the DRX cycle, there are certain parameters. So the 3 parameters that have been considered is the length of the DRX cycle. So like every 60 milliseconds, you basically discretize the time in this cycle. You have a start offset that define when your on duration starts with respect to the start of the DRX cycle. So the user will activate after start offset millisecond. And then you have when the on duration ends, let's consider the cycle n+1, you enter in the off duration. So if you have a scheduling decision that is sent on the control channel when the user is off, well, basically you cannot schedule the user. You have to wait until the next DRX cycle. And this introduces an extra delay and make more challenging to satisfy the user. So you see why there is a trade-off between capacity and power saving, because the longer you put in off period the user, the higher is the probability that the frame arrive when it's off. So you cannot schedule the user. You need to wait until the next DRX cycle. There is one thing that helped, that is the inactivity time. The inactivity time is triggered when the scheduling information is received. So let's assume that during the on duration, the user receives scheduling information for a fragment of the entire frame. Then he will stay on for a certain value that is a parameter of the system, and will enter in off after the end of the on duration. So eventually, if you have frames that arrive, for example, in the middle of the inactivity timer, if the on duration is over, the user is still active and you can still get the frame. The thing is that you need to have at least one reception here. If the frame arrives here, the inactivity timer will not be activated, and in that case, you lose. So we have considered different schemes. These are the main three parameters, and the direct configuration that we have considered was the first value is the duration of the DRX cycle, so 16 milliseconds is the duration, similar to the 16.66 milliseconds of average arrival time. 8 is the on duration timer, and Z is the inactivity timer. So in the first case, you have half of the time the user is on, and possibly half of the time is off. In the second configuration, we have considered 10H2, so you have just 2 milliseconds out of 10 at most in which the user is off. And the last one is 10.5 milliseconds at most in which the user is off. So the capacity in downlink, you can see, of course, always on is the baseline that was considered. So we know what is the capacity of the always on, and then we test that number of user with the DRX configuration on. And you see that in the case of 1688, the capacity go to 0. Doesn't mean that you don't have traffic. It means only that the user get delayed more than 99% of the frame, and therefore they cannot be satisfied according to the KPI. You have still traffic, but it's delayed more than this 10 or 15 milliseconds. For cloud gaming, still the 15 milliseconds help you, because this 15 milliseconds for the 1688, if you have 8 milliseconds at most in which you are off, you have still 7 milliseconds of on in the worst case, in which you may be able to satisfy the user. But when you have a lot of traffic, a lot of user, it becomes more challenging. You have also queuing that you have to consider, and then you may have retransmission. So eventually this lost 8 milliseconds have an effect.
How long does the transmission takes? Milliseconds?
A couple of milliseconds, a single transmission, but then you have the acknowledgement. If you don't have an acknowledgement, you will have other retransmission that take place. So the transmission is not considered satisfied until the whole frame has been transmitted. And then yeah, the same kind of results you see that also this 10.5.5 actually by reducing the time the user is off, so introducing more frequency in the sampling of the control channel, reduce the capacity loss. The problem is that when you reduce the on duration, actually here it's easy to explain. So the length of the off duration define also the state, the sleep state in which the user can enter. So if there are 3 sleep state with different power saving, and if you want to enter in the deeper sleep mode, you need to extend more than 80 milliseconds the off duration. Otherwise, you save less power. Even if the amount you distribute your amount of on period over time, and then you say, I took just 1 millisecond on, 1 millisecond off. It's not even possible, but let's assume that it would be possible that in any case, the device cannot enter in a deeper sleep mode, so you will consume still more power. I will skip this because anyway, they conclude all the same solution. This was for uplink, is a bit different, but for downlink, in all the cases you have it that this 16.8 is not actually satisfied user. So since you have this basically arrival with this jitter, what we have considered was to introduce some adaptation in the DRX cycle. So instead of considering the DRX cycle fixed, now we introduce some flexibility in configuring in an online fashion the DRX cycle. So basically the system learn what is the best DRX configuration for the different user, and they will adapt accordingly to the frame arrival. So you have basically this, you know the jitter of your frame. So the idea is that what you want to have is to find the best on duration in such a way that you satisfy the 99% of the frame. That means that you want to you want that the on duration is slightly larger than yeah. Okay. So I will go fast here. So basically you see that the 2 extreme are, you have a very short on duration, but you cannot satisfy the user almost certainly. And instead you have a long on duration, you satisfy always the user, but you spend more power. So, okay, we modeled the problem and eventually we evaluated. So I will skip all this part. Maybe the interest part here. So these are the black line is the always on, the green line is the CDRX configuration with 16.8.8, and then you have these DRX that instead learn over time what is the best configuration and then apply the best configuration to the user, and they keep that configuration. Actually keep learning, but then since it's stabilized over time and we have proved that you can stabilize the queue, then it will converge to the best solution. So basically what you have is that you see that when you move from the left to the right is from cloud gaming with 15 milliseconds to 10 milliseconds, you see that the fixed configuration, of course, becomes worse. We have already seen you are not able to satisfy any user according to the definition. Instead, when you're using this dynamic approach, you are able to recover part of the capacity. What you lose, of course, is in power saving because you tend to extend a bit the on duration with respect to this 16.8.8. It's not for all the users the same. For certain users becomes shorter, but for many becomes much larger. They are almost always on. So that's actually affect eventually the average power saving gain. But the distribution of this gain is more in a certain way fair according to the arrival of the traffic. And another thing that is worth mentioning is that this bound here for the DRX configuration is it's valid only for the cloud gaming services, not valid for the AR and VR because there is no user satisfied. So you cannot really say that there is a power saving gain in that case. So you can actually adapt. We are working also on some other evolution that would actually help to increase even more that power saving gain. But actually the idea of having something that is more dynamic actually helps a lot for this type of services. So just to conclude, for takeaway, XR traffic is a type of traffic with very high throughput and require low latency, but it's still different from IoT. So it's not, we cannot reuse the same type of feature that have been designed for IoT traffic for XR traffic. Power saving has a huge effect on the capacity, on the number of satisfied users, as we have seen. So there is room for improvement of power saving feature in NR. And also for the capacity, what we have noticed, I haven't discussed much about this, but the application awareness, we have mentioned it a bit, this when we were discussing about the scheduler. It's actually something that can help improving the capacity in terms of number of satisfied users. And another challenge is that is really a cross-layer problem. So the problems span multiple layers, and you need to have this information that flow across layer if you want to really optimize the network. So I have concluded my presentation. Thanks everyone.
Thank you. Short time for questions. Any question in the room?
Yeah. So two things. I mean, the first one, you didn't allude to bandwidth part. I mean, does it make sense to, since these are very large, to
there were discussion also. Yeah, this is good observation, because there were discussion to reduce also not only the bandwidth but also the resources allocated to the user in such a way that you reduce basically the consumption of the user. So you reduce basically the power, so the bandwidth. So eventually, you need to you improve your performance because you need to monitor a smaller bandwidth, so you need to make measurements of smaller bandwidth. That there were discussion also about that, but eventually the focus was mainly on other power saving features. But yeah, there are discussion on this line. It's a very good observation. In particular for uplink, because for uplink the user is limited in the amount of power. Yeah, and he cannot use the whole bandwidth, and if you provide him the whole bandwidth, eventually he cannot use the whole bandwidth, but you have to measure all bandwidth to provide reporting to the G0V. So eventually this will affect the power saving. Yeah. Yes.
And I mean, another different question is, I mean, so here you assess what happens there, but what is the effect of these guys, of these applications on the rest? Is it, I mean, they are the usual users, right? So yeah. This is a shared medium. So
yeah, exactly.
Does it make sense to, I mean, include the effect of this huge,
yeah, of course. Then usually in network you have class of priority for the different services, and usually it's like creating slices, no? So you dedicate all the resources to this certain class. And of course, you will have an effect on the other type of traffic. That's also something that is important to take into consideration.
Yeah, not to speak of the things that come from other cells, right?
Yeah, exactly, because you will also affect other user. Yeah, if a cell is there is no user and XR traffic user, you have eMBB traffic, this will be probably affected because you are using the bandwidth all the time for the transmission. Therefore, you are generating also a lot of interference to the other cells.
Yeah. And you must then ask the same type of questions: how many guys you may satisfy this XR type, given quality constraints? Quality constraints on I mean, that you don't crush
the other
the small guy.
Yeah, true. Yeah, that's true.
Right. So, okay. Thank you.
Any question for people connected? Time for a very last question in the room. No questions, so thank you again.
Thank you very much.